So good morning, everyone. Thank you for being here this morning, and thank you to the organizers for giving me the chance to present here. So what I'm going to try to very briefly summarize this morning is some key results from a series of papers that we put out last year working together with a lot of people here in Santa Cruz and also within the Candles collaboration. And all of these papers focus on the same key problem, which is trying to find what are the progenitors of the massive, extremely compact quiescent galaxies that you see around cosmic noon, around CO2, the so-called red nuggets, called that for obvious reasons. So we're trying to investigate a little bit more in detail how quenching takes place at high redshift and what is the formation of the first elliptical galaxies that they will evolve and we see in the local universe today. And in particular, we want to look for the immediate progenitors of these red nuggets and investigate what is the possible connection to the other family of massive star-forming and disturbed-looking galaxies that Ich and Anir were talking about before. So let me start with some very basic introduction. The idea of trying to look for galaxies that go from star-forming to quiescent is certainly not new. And it's fueled by this strong bimodality that you can see there in the color, star formation rate, specific star formation rate. So you will always have galaxies in blue cloud, red sequence moving from one to the other. So what we wanted to do is see if we could refine somehow this process of looking for progenitors. And in particular, we wanted to make use of the Candles data. So the with-3 infrared imaging by HST that gives you a fantastic resolution in the optical rest frame of these galaxies, and then you can have a look at the structural properties just like Eugene was showing about the clamps of the galaxies. So we wanted to take advantage of this to look at the structure of galaxies, and the relevant property that we wanted to throw here in the mix to select these progenitors is the mass-size relation. And we know that today that star-forming galaxies and quiescent galaxies follow fundamentally different mass-size relations, so that for a given stellar mass, your quiescent galaxies are typically much smaller than the star-forming analog. And not only that, so we know that they follow, we can trace their mass-size relation up to very high redshift, so we know that their difference are preserved even at redshift of 2 or even redshift of 3. So we wanted to combine information from these two diagrams, and we can do something like this. So we can look for the property that is the most orthogonal to the bimodality. So in the diagram in the left is pretty simple. You can go with the specific star formation rate or the color, and you can look for some sort of green valley threshold, and you can call it star forming and quiescent. This is more or less what people have been doing in the past, and then you can have a look and try to do the same in the mass-size relation, and then you will get something like this line that more or less divides the two populations. And you get something that is some sort of pseudo-mass surface density or surface brightness. And the reason for this strange 1.5 is basically that we know today that the mass-size relation of quiescent galaxies has a remarkably constant slope, and you can have either 1.5 or if you do r to the power of m, it's like 0.7. But it's a remarkably constant slope that seems to be preserved from redshift 3 to redshift 1, more or less. So by virtue of picking a line that more or less follows the slope of the mass-size relation of quench galaxies, you can reduce the scatter. So if you use this relation, then all of the quench galaxies will line on your y-axis, and they will follow closely that relation. So let me explain that in a bit more detail. You have these two diagrams, and then you use your threshold in a specific star formation rate that will be your y-axis. And then you pick this mass surface density, the pseudo-sigma, and this will be your x-axis here, right? So what we do is that we will call galaxies that are to the left of this line compact. So they're dense, they're high surface brightness, and these are essentially galaxies that follow the mass-size relation of the quiescent population. And then we will call the other ones extended, and of course we'll call star-forming and quiescent at both sides of the green valley in the specific star formation rate. So in this cartoon world, it's a pretty simple picture. You will only have star-forming galaxies that are all extended. They're here in this bottom left box, and you will have quiescent galaxies that are all compact. Obviously, this is not what happens in reality, and we know that to end up here, you were a star forming at some point in your life, so how do you end up in that box, right? This is the question that we want to address, is what happened to you? You were perhaps a star forming disk that you start making a bulge, you become more centrally concentrated, the star formation goes out in the external parts, and then it appears to shrink in the light profile, so galaxies appear to become more compact and centrally concentrated. Or alternatively, you can have galaxies that experience some sort of dissipational transformation. They have a major merger, and then they make something like a compact Riemann. But they're still star forming. They're making a lot of stars as a process, in the process, and then they quench and go up. So this is the simple question. You, of course, can have something in between, but I'm just showing the extreme possibilities. Okay, so To address this question, we use the candle sample. We select galaxies around redshift 2 to 3. Only the more massive galaxies that were more massive than 10 to the 10. We use the photometric redshift, star formation rates, and we measure the light profiles using the candles width free data that gives you the rest frame optical of these galaxies. And the answer, or at least what the data suggests, is that galaxies will follow an evolution that will go from extended and star forming to compact and star forming, and then they will quench and go up following an evolution like this. And you can see here in the color postage stamps that combine ACS with width-free imaging that the compact star-forming galaxies look remarkably similar to the quiescent galaxies, but they look very different from the other extended star-forming galaxies. In fact, if you look at these two populations, I can probably move some galaxies up and down that you wouldn't even notice. They look remarkably similar in their colors, and that is because these are red quenched galaxies, and these are extremely dusty star-forming galaxies. So in the optical colors, they look very red, but if you can study in more detail the star formation rates, you can see that they are significantly different. So if you look at these two diagrams that here show the main sequence, so it's a star formation rate versus mass, you can see that the blue extended and the green compact galaxies, they both live in the main sequence. So they're strongly star-forming, whereas the quenched galaxies live here in the death sequence, if you like. But when you look at the mass size, the extended galaxies follow this distribution that is the mass size relation of extended galaxies, while the compact star-forming galaxies seem to live in the mass size relation of the dead guys. So they're star-forming, but they're significantly more compact, and they really look in their structure like the quenched galaxies. So it suggests that the evolution will go like this, because you have very few or almost no galaxies here, so they will become compact first, and then they will quench. And let me show you this in a little bit more detail. This is redshift 2 to 3. I'm going to split this in several redshift bins so that you can see the evolution. And these redshift bins more or less show you a similar comoving volume. So the number of objects more or less correspond to a number density. So we go here from redshift 1.8 to 3. And the first thing I want you to look at is the quench box, right? So these are all compact quiescent galaxies. At redshift 3, you have very few. This is good because at some point you have to run out of quench galaxies. You have the first at these redshifts. There are very few, and as you go to lower redshift, you keep making more and more of these galaxies. So you are building up the red sequence here, and you can go up by a factor of 10 or so. So they grow very rapidly. You are making a lot of these galaxies, and if you're seeing they're going down, they're going up, they're quenching, they're here, they're compact star-forming galaxies quenching and going up, and then you look at the number density. The number density in these three boxes doesn't change that much. So if you believe this picture, then all of these galaxies evacuate this region, they quench and go up, but then you will need another mechanism that keeps populating this box. So you will need two flows, one going up, this is the more reasonable, so these galaxies quench and go up, they have a similar structure, masses, then you need another mechanism to keep moving galaxies from extended to compact star forming. Okay, so this is now with a proper number density, again, the same flow of galaxies. And before I forget, I will also like you to pay attention a little bit here at the stars. There are markers that indicate the X-ray detection, and this is something that Dale presented yesterday, is that many of these compact galaxies above redshift of 2 seem to be X-ray detected, seem to host an AGN that we do not know at this stage if it's responsible for the quenching, but at least tells you that maybe it's related with a rapid growth phase in the galaxy or in the central core of the galaxy that was feeding, not only making a lot of stars, but also feeding the AGN and making the AGN bright and luminous so that you can detect it in the X-ray. So which way would you like to go? This way up? Oh. So you like them to be compact from the very beginning, but not so massive, and then they just appear here in this box, right? So you say they're not detected, and they appear there all of a sudden. So this is, I mean, our threshold goes down to 10 to the 10. So we pick all of those galaxies, and we see that they are here. So we detected in this box. We may lose a few of them if they grow very fast, but it's unlikely that all of them are going to pop up here very rapidly, because even in these time stamps, it's true that you don't have that many galaxies, but you should be able to see them appear. I mean, in a reasonable time step. So in roughly 200 to 300 million years, you won't have time to make that much mass on a 10 to the 9 galaxy to go to the 10 to the 11, right? It would be, I mean, they have to be submillimeter galaxies. That could be another explanation. But then there will be extended things here. But there are other possibilities. Okay, so going back to the number density, so Here, the red squares are the quenched galaxies increasing from redshift 3 to 1.8 to 1 by a factor of 10 or so. We feed that with a red line, and we make a simple test, and we say, okay, let's say that this is a cumulative distribution of a population of star-forming galaxies that quench in timescales of 300 million years to 1 gigayear. They quench, they die, and they make the first quenched galaxies. You kill a few more of them, then you add that, and then you keep building up this number. So if the population of compact star-forming galaxies quench in a time scales of roughly 700 million years or so, you can build up this red line. So it falls in between these two time scales, and it's more or less a good match. So in principle, if all of these galaxies quench in these relatively short time scales, you can build up this number here, but you will, again, need another mechanism to keep this number here constant or increasing. So let's say that you believe this part. I think it's quite compelling just by looking at the structure and the properties of these galaxies that they can quench and go and make the quiescent population. You still have the problem as how do you make these galaxies in the first place. So I'm not going to talk a lot about major mergers. This is the classical approach. You've seen this many times. You can, in principle, merge two of these galaxies. You have a lot of dissipation and make a compact remnant. I'd like to talk a little bit about disk instabilities. You already see some results this morning talking about clamps. So Nir, Ethan already talked about that. And Adi is going to talk about that as well later. But I just want to say that at this redshift, we know galaxies have a lot of turbulence. They are creating a lot of gas. They may become unstable and funnel not only a lot of gas, but also stars and clamps into the center and build a compact core. So we wanted to take a look at the possibilities and how that would affect the number densities that we calculate. And we're starting by having a look at semi-analytic simulations. So these are an updated version of the semi-analytic models of Rachel Somerville that Lauren Porter, that was a student here with Joel and Rachel, update. And we asked her to produce a simulation and a video showing where in their simulations will be the compact galaxies and how they will evolve in time. And the particular thing about these stamps is that they include a prescription for disk instability. So they can have galaxies that experience a disk instability and become more compact. They transfer mass from the disk into the core of the galaxy. And they didn't do it just to study the evolution of our galaxies. In fact, they do it, and you can see in these two papers that are already submitted, is that they needed to when they look at the stellar mass function of galaxies in the local universe, they couldn't reconcile the number of disks and spheroids. So they needed to have another mechanism to produce spheroids instead of quenched disks. And so they added this prescription that worked very nicely for the local universe and this morphological breakout of the mass function. But it also worked quite nicely for the galaxies at high redshift. So what I'm going to show you here is the evolution of galaxies that are going to be compact and start forming at redshift 2, and they're going from redshift 5 and down to redshift 0. And the movie is going to repeat again, but you can see that it looks very similar to the evolution that we were suggesting. And every time you see a blue flash here, shows a galaxy that experienced a disk instability in the past. So not all the galaxies experience a disk instability to become compact. Roughly 40% experience a major merger, but then it's nice that you can have two channels, two mechanisms that will make galaxies compact and go into the compact star forming region, and then quench and go up. And then, of course, you can also see how some galaxies become more extended at a later time because of gas-poor dry mergers. So you can also move back and become more extended at later times. But we're in particular interested in what happens at high redshift and how do you make the compact galaxies. We can also have a look at the hydro that you have been looking at this morning. And these are some of the Severino and Deckel simulations. And again, Adi is going to talk about this a little bit more later. But in our paper, we just wanted to focus on the question of whether can you make something that is significantly more compact due to a disk instability. So out of all of the galaxies that we have in the simulation, we just picked the three most extreme examples of galaxies that will evolve in the mass size relation. And here you can see two black lines that show the evolution of two of these simulations that basically grow in mass and size. They fluctuate a lot because they have a lot of ex situ clamps or some in situ clamps, and then the effective radii of the light change by a lot, but they fluctuate, but overall they grow in mass and size. But we found three examples of galaxies, these three here, that go from a disk phase, where they're actually extended nice disk with a lot of clamps, indicating that there is some instability going on. And they will go from this extended phase to this compact phase down here, where they will shrink by a factor of 2. And this is exactly the same galaxies. There's no major merger going on. And you can see that they become significantly more compact and they increase the mass surface density. Of course, this is not a complete sample of how all galaxies will evolve at high redshift, but we at least find 3 examples that this can happen, and that just the disk instability, not a major merger, can make a galaxy more compact without having other companions around and requirement for a merger. Okay, so then let me go one step back and talk a little bit more about the properties of the compact star-forming galaxies. I already said that they are actually quite red, just like the quenched galaxies, because they are dust obscure. And here I'm showing you again the main sequence, star formation rate versus mass. And all of the blue markers are compact star-forming galaxies. And the different colors indicate detection either in MIPS or Herschel. So the dark blue points indicate detection in the far infrared. They are strongly luminous in the infrared. 70% are then dusty star-forming galaxies. Only 2 of them seem to be slightly elevated above the main sequence, so the bulk of the population. So they seem to be like normal main sequence galaxies that go in, they're making a lot of stars in a dusty mode. 50% are AGN, so again, all the stars are X-ray detected galaxies, just like they was telling you yesterday. And some of them are also going down below the main sequence in a nice transition within that is going from the main sequence to the dead sequence. So many of them are already in their way down to quench. Again, we also check about the mass distribution, the axis ratio distribution, and the CERSEC distribution of these compact star-forming galaxies compared to the quiescent population. And you can already see the mass range already fits quite nicely. So we're not talking just about galaxies that are more massive than 10 to the 11. We're talking about basically all quenched galaxies around redshift 2 to 3. So more massive than 10 to the 10. You don't have that many here, but you have a range in stellar mass that matches quite nicely that of the compact star-forming galaxies. And the axis ratio and the CERSEC index that are typically above 2 or 3 also are very similar to that of the quiescent population. So the next thing that we wanted to try obviously was to follow up these galaxies with near-infrared spectroscopy to see if we can get a better handle on star formation rates, maybe metallicity, excitation diagrams. So I'm showing you again the star-forming main sequence here, and only now the blue, dark blue markers are the compact star-forming galaxies, and these cyan points are other star-forming galaxies that we got in our sample for near-infrared spectroscopy with MOSFET. That is the multi-object near-infrared spectrograph in Keck. So in this diagram, I also wanted to highlight these gray markers that are previous samples observed in near-infrared spectroscopy. So there have been already quite a lot of surveys trying to investigate the star formation rates or the properties, the kinematics of galaxies at redshift 2. And you can see that they all more or less probe the main sequence, just like we are doing with our sample. But if you look at the mass size relation, basically all of the galaxies that were studied in the previous surveys were focused on the extended, larger, sometimes disturbed, clumpy galaxies that, for example, Yichen was talking before. So none of the previous surveys was specifically looking like we do for the most compact galaxies at a given stellar mass. So we're just focusing on the compact star-forming galaxies that were previously underrepresented in other surveys. But just to compare to other surveys, we also got quite a few of other extended star-forming galaxies so that we can compare their behavior to the compact star-forming galaxies. Okay, so here are a few of the spectra. Here just again the postage of the galaxies that look quite red. This is the 2-dimensional spectra. This is the 1D extraction. And as I was saying, there are many things that you can do with the emission lines. But the first thing we notice immediately by looking at the spectra is that the lines are quite broad. So this translates into a velocity dispersion of roughly 230 kilometers per second. That's the median of the sample, but you can have galaxies that go up to 300 or even more. So at the beginning, we were surprised by this, but then if you think about it a little bit more in detail, I'm showing you again here the mass size relation. And if you use the virial theorem and you use this velocity dispersion and you look at the effective radii of these galaxies and the stellar mass that they have, assuming no dark matter, no gas, just by looking at the stellar mass of these galaxies, and you use the effective radii, this velocity dispersion that you expect for these galaxies is actually of the order of magnitude of 200 kilometers per second or so. So all of these galaxies in the green line here, assuming that they have the same virial coefficient, they will lie in this line. So it's not unreasonable, and in fact, if you look at the quiescent population, there have been many studies already at redshift 2 looking at the velocity dispersion of quenched galaxies, and they actually find these velocity dispersions of the order of a few hundred kilometers per second. So we're finding the same in the gas, in emission, for the compact star-forming galaxies. So again, now you can put the different samples together. The gray markers are the different samples from the literature, And here are the quenched galaxies, where the velocity dispersion is actually computed from the stars. And all of these are computed from the gas. Here are our extended star-forming galaxies and other extended star-forming galaxies from the literature. And you can see that the velocity dispersions, can go a little bit above 100, but they're typically lower velocity dispersion for the stellar mass that they have. And when we overplot where the compact star-forming galaxies are, they actually match quite nicely the velocity dispersion of the quenched population. So not only they have the same mass, surface brightness, profile, CERSIC, they also have similar velocity dispersion, and if you're willing to believe the gas and stars are actually probing the same potential, they actually have similar kinematics. Telling you that basically all these galaxies have to do is basically quench and turn into the red nuggets, the quiescent population here. Okay, so this is my last slide. This is just a summary, a cartoon version of the picture that I was showing at the beginning. If you can only take one message home, is the galaxies, at least at the high redshift domain, become more compact before quenching. So they become compact cores that are still star forming. They're very red and dust obscure before they quench star formation. And we think this process goes as some dissipational process will make the galaxies more compact. Perhaps they were extended, perhaps they were very compact at the beginning. We don't really know, but there must be some sort of dissipational process that keeps moving galaxies into this box. Then they quench here. They tend to have a large AGN fraction that, again, we don't know if it's responsible for the quenching or they're just along for the ride, but it's consistent with the number of AGNs that you will find later in the quenched galaxies. So it's reassuring that you are still finding these AGNs in the precursors of these galaxies, because you really need the AGN at the later stage. So they will quench and go up in what we call the fast track of quenching at high redshift, and I didn't have much time to talk about this at lower redshift, but there are many papers out already. You can have a look at, so Jerome and Edmond already have some papers out talking about that, where you will have other extended galaxies just fading. So these galaxies making a bulge and this fading and quenching while they're still extended. So you don't have necessarily to make something compact before you quench. You can quench and go up like this. And in fact, this contour shows the median evolutionary trend at redshift below 1 in our catalog. But at high redshift, you will make a compact core first. And they're typically very dusty, and they have a lot of AGNs in there. And I think I'm going to stop here then.
Okay, so I agree entirely that the compact star-forming galaxies are an excellent possible progenitor population for a compact galaxy. I guess the cartoon is something that always seems a little bit premature.
Okay.
In the sense that at least almost all previous galaxy formation models easily manage to make, so you can have mergers that do actually all of this in previous versions of Semiotic models,
yep.
etc. So the relative ratio of disk instability in mergers is, I think, still pretty uncertain. Also at low redshift, this slow track does not need to be slow. One expects that mergers between galaxies, which are not ridiculously gas-rich, should do something that acts a lot like that. It's a relatively fast process, but it happens over an extended period of time, and so it looks like a slow buildup of the population. So I know Sandy and I agree to disagree on this.
Yeah.
Well, maybe she doesn't agree to disagree, but I'm happy to disagree with her on it. I don't know that one has to appeal to, in fact, I'm pretty sure that one should not just appeal to disk fading, etc. as a way of making
you can definitely have mergers. So it's about.
Well, the point is mergers happen, actually, so we have to figure out how to deal with them. The hierarchy does this, and so we should, to not incorporate that in our intuition is...
So I think there are two different things here. I'm not opposed to have mergers at any of the slow or fast track or high redshift, low redshift evolution. And we're not sure, so we're just quoting disk instabilities or mergers as possible scenarios because it's nice to have different possibilities to make these compact galaxies, because we see that you are making a lot of them, and we don't really know how that happens. So in our side, we're just showing the observer's perspective to this, and then we have to account for these galaxies that are appearing and then quenching. And then at low redshift, I think the only thing that I like to point out is that some of these galaxies that will go in what we call the slow track is that they've been forming stars for a long time. Maybe the quenching could be something fast. It's the overall life of this galaxy. So they live for a longer period of time, whereas the other ones, maybe they form and quench rapidly. So that's this, they live a short life. How fast they quench in the last part of their life, that's something that is open to debate. I agree with you.